Alright, in this video we're looking at section 5.4, conditional probabilities and the general multiplication rule. So you can see our objectives there, but let's start off where we left off in our last section. So we learned that when two events are independent, the occurrence of one event has no effect on the probability of the second event. However, you can't always assume that two events are independent. So think about this scenario. Will the probability of being in a car accident change depending on your driving conditions? Now, I would expect that the probability of an accident will be higher if you're driving on icy roads versus driving on dry roads. So the probability of getting in an accident and driving on icy roads is probably going to be different than the probability of driving or getting in an accident driving on dry roads. And so the conditions of the road could be very, or the likelihood of an accident could be very dependent on the conditions in the road, and vice versa. So let's look at this example. So according to some data from the Centers for Disease Control, 33% of all adult men in the United States are obese. So the probability is 0.333 that a randomly selected adult male is obese. You just randomly pick someone in the United States. However, 28% of adult males ages 20 to 39 are obese, compared to 40% of adult males ages 40 to 59. So the probability is 0.28 that an adult male is obese given that their age is 20 to 39. But then it's 0.40 that an adult male is obese given that his age is 40 to 59. So the probability that an adult male is obese changes depending on the age group. So obesity and age are not independent, because when you change the age group, it changes our probability. So one definitely affects the other. So these are dependent events, and we call this a conditional probability. So one word to hone in on is given. You'll hear given quite a bit. And that just means that something has already occurred. So the notation is the probability of F, and then that vertical line means given E. Okay. And it's the probability of event F occurring given that event E has already occurred. So that would be the probability that someone is obese given that their age is 20 to 39. Would be how we read that. Okay, here is the conditional rule for probability. If E and F are any two events, the probability of F given E is the probability of E and F divided by the probability of E, or the number of outcomes in E and F divided by the number of outcomes in event E. Okay, and then that's explained in the text there below. So, suppose that E and F are two events, and that the number of outcomes in E and F is 420. The number of outcomes in event E is 740. What's the probability of F given E? So the probability of F given that E has occurred is just going to be the number of outcomes E and F divided by the number of outcomes in E, which is 420 over 740. Okay, and this does reduce down, in case you're curious, to 21/37, where's the decimal? 0.568. So there would be a probability of event F given E is 0.568. Now we don't know anything about E and F in this case, but that's just how the calculations will work. Now notice if I do the probability of F given E equals the probability of E and F over the probability of E, okay, just from this rule right here. If I were to take that, and if I were to multiply both sides by the probability of E, okay, notice that I get the probability of, now I've solved for the probability of E and F. So the probability of E and F is just the probability of E times the probability of F given that E has occurred. And hopefully this looks like our multiplication rule that we were doing in the last one. So just as a note, when things were independent, okay, the probability of E and F is the probability of E times the probability of F when they're independent. However, here we can see the only difference is that probability of F is now the probability of F given E. That's our general multiplication rule, because it's possible that things are not independent. So independence occurs when the probability of that second event is the same as the probability of the second event given that the first event has occurred. That's when we identify independence. Okay, I just want to make a parallel there. I'll have it formally outlined here in just a bit, but just so you can see the difference. But this is a great rule to know. The multiplication rule, again, and goes with multiplication and probability. And that will be on your formula sheet. So let's look. We want to suppose that E and F are two events, and the probability of E is 0.4, probability of F given E is 0.6. What's the probability of E and F? So again, remember the probability of E and F is the probability of E times the probability of F given that E has occurred, which is 0.4 times 0.6 or 0.24. Yet again, we don't know events E and F, what they are. We're just using the rule. We're getting comfortable with it when we're given some numbers, because we are going to have some story problems. Now, with independence, I do want to make one comment. If small random samples are taken from large populations without replacement, it is still reasonable to assume independence of these events. Okay, we're going to be using this idea later on, but just wanted to mention it here so that it crosses your brain. So just as a rule of thumb, if a sample size is less than 5% of the population size, we treat events as if they were independent. That's going to come into play not much later on, but it's a little bit later on. But just know when we talk about independence, we are going to be making sure that this claim, less than 5 sample size, less than 5% of the population size, we're going to be bringing that into play and verifying that several times. Okay, now as I mentioned before, two events are independent if the probability of E given F is the probability of E, or the probability of event F given E is the same as probability of F, meaning that just because one thing has happened, it does not affect the probability of the original. Okay, and that's how you can confirm that our definition for the multiplication rule of independent events is true based off of what we saw. It's just a special case of the general multiplication rule. Okay, so in this question number 10, then we have the probability that a randomly selected individual in the United States 25 years and older has at least a bachelor's degree is 0.094. So we'll say the probability of a bachelor's is 0.094. The probability that an individual 25 years of age and older has at least a bachelor's degree, and then now we've got this little thing, given that the individual lives in Washington, D.C., is 0.241. So this is the probability that bachelor's degree given that they live in Washington, D.C., is 0.241. Are the events bachelor's degree and lives in Washington, D.C. independent? Okay, well, notice if they were independent, these two probabilities would be equal, meaning that, given that someone lives in Washington, D.C., the likelihood of having a bachelor's degree for someone 25 years and older, that given in Washington, D.C. should not affect B if they're independent. However, the probability of a bachelor's degree is not equal to the probability of a bachelor's degree given that someone lives in Washington, D.C. And when they are not equal, this means that they are not independent. Okay, so that's just a quick way to check that. Just check the conditional, and if they're not equal, then they're not dependent. And I don't know the whole reasoning behind the why on that, but that is just based off of some data. Now let's look at drawing a card from a standard deck of cards. So suppose that a single card is selected from a 52 card deck. Okay, this is where we got 4 suits, and so we got hearts, diamonds, spades, clubs, and we want to know what's the probability that a king is selected. So the probability that you get a king, well, there are 4 kings out of the 52 cards, which reduces down to 1/13. That's the probability of getting a king. Now, let's change that around. What if we're told that the card is a heart? Like you've got a card in your hand, you don't know what it is yet, but your friend is looking at it and says, the card is a heart. So you know that. What's the probability of drawing a king? Whether that card is a king. So now we want to know what's the probability that you get a king given that the card is a heart. You already know that it's a heart. Well, there's 1 king out of the 13 hearts because the hearts are 1/4 of the deck, or 1/4 of 52. And 1/4 of 52 is 13, so there's 1 in 13 chance that you get a king given that you know it's a heart. Well, notice those probabilities are the same. The probability of getting a king is the same as the probability of getting a king given that you know the card is a heart. And this idea tells us that the 2 events are independent. Whether you're drawing from the whole deck or whether you know that it's a heart, what's the probability of getting a king, that actually doesn't matter. You get the same probability. So they are what we call independent events. Okay. Now, let's look at some weather here. Rainy days. So for the month of June in the city of Chicago, 37% of the days are cloudy. So the probability that we are cloudy is 37% or 0.37. So also in the month of June, in the city of Chicago, 21% of the days are rainy and cloudy. So the probability that it's cloudy and rainy is 0.21, 21%. So what's the probability that a randomly selected day in June will be rainy if it is cloudy? So we want to know what's the probability that it's going to be rainy given that it's cloudy. Okay, well, remember that the probability that it's cloudy and rainy is equal to the probability that it's cloudy times the probability that it's rainy, given that it's cloudy, using our general multiplication rule. So that's a P for probability there. Well, now we can substitute in. We know that the probability, my app just froze. Hang on one sec. Okay, we've revived the iPad here. So now we're going to make some substitutions. Probability it's cloudy and rainy was 0.21. The probability that it's cloudy is 0.37. And then times the probability that it's rainy given that it's cloudy. That's what we don't know, but that's what our question is asking. So we're just going to divide by 0.37 on both sides of our equation. So when I divide those out, I get 0.568 is the probability that it's rainy given that it's cloudy. Okay, so that's how we would use conditional probabilities there. So that'll wrap us up for part 1. But hopefully it's making sense. If you got any questions, let me know.